Welcome to today's Explainer. I am so excited to have you here. Think of me as your mentor today because we're going to demystify exactly how we build practical, powerful AI projects from the absolute ground up. If you've ever felt like deep learning is just this impenetrable wall of math, well, we're going to break it down together piece by piece using this exact blueprint. It's the ultimate question, right? How do we go from a single, basic mathematical formula to a genuinely intelligent system with billions of parameters? Systems that can understand human speech or generate mind-blowing art? Today, we're popping the hood. We're going to unpack that black box and see exactly how these models learn, adapt, and eventually outperform even the expectations of the people who built them. So here is our roadmap for today. We'll start with the deep learning landscape, then architect the network, explore the sheer power of nonlinearity, break down the mechanics of backpropagation, navigate tricky loss landscapes, and finally, look at generalization. Let's get into it. Section 1. The deep learning landscape, scaling from cloud to edge. Now there's a massive contrast in how we deploy AI today. On one side, you've got traditional setups. We're talking massive cloud GPU data centers powering giant models like GPT-4, which literally cost hundreds of millions of dollars to build. But on the flip side, that's today's reality. By optimizing our training for consumer-grade hardware, we can actually run highly capable open-source models locally on edge devices, literally on your phone, completely offline, even in airplane mode. It's wild. And we're moving far beyond just text, too. Modern deployment is shifting heavily toward end-to-end audio and vision models. So instead of taking speech, converting it to text, processing that text, and turning it back into speech, these new models process the raw audio directly. Because there's no round trip to the cloud, the latency is incredibly low, and crucially, the model actually captures raw human emotion. Section 2. Architecting the network, the building blocks.
Okay, so every neural network starts with a single foundational building block, the perceptron, and it operates in 3 core steps for forward propagation. First step, we compute the dot product, meaning we just multiply our inputs by their weights. Second, we add a bias term. Now, this bias is absolutely crucial. It allows the model to shift the activation function left or right, giving the neuron the actual flexibility it needs to fit the data. And finally, step 3, we apply a nonlinear activation function.
So what happens when we scale that up? Well, deep networks are essentially just stacking these individual layers on top of each other. But it's this exact stacking that enables hierarchical feature extraction. Unlike a simple linear model, the first layer here might just detect, say, basic lines and edges. Deeper layers compose those lines into corners, then maybe eyes, until those super simple inputs are transformed into highly complex representations, like a full human face. Section 3. The power of nonlinearity, drawing the curves. You see, without an activation function, a neural network mathematically collapses into a series of purely linear transformations. It would literally only be capable of drawing straight lines. But as we know, real-world data is messy, it's dynamic, and it is highly nonlinear. If you try to separate complex data points with just a straight line, your model will completely fail. Nonlinearity is that vital ingredient that empowers the network to draw those curved decision boundaries. To draw those curves, you essentially have 2 primary tools, sigmoid and ReLU. If you need your model to output a probability, like a simple binary yes or no classification, you're going to use the smooth S-curve of sigmoid because it constrains any input into a neat range between 0 and 1. But for hidden layers, ReLU, or rectified linear unit, is the modern standard. It outputs values from 0 to positive infinity. It acts as 2 linear functions joined by a nonlinearity, making it incredibly computationally efficient while enforcing non-negativity constraints. A real game changer. Section 4. Backpropagation mechanics, the learning engine. Ultimately, it all comes down to backpropagation, which honestly, in theory, is nothing more than the chain rule from calculus. Once the network makes a prediction and calculates its error or its loss, we use the chain rule to propagate that error backward through the network's topology. It basically decomposes complex derivatives layer by layer, multiplying them together to figure out exactly how much each individual weight in the network contributed to that final loss. And that tells us exactly which direction to adjust our weights. Section 5. Navigating loss landscapes, optimization. Knowing the gradient just points you downhill. But how big of a step do you actually take? Traditional vanilla gradient descent uses a fixed learning rate. And the problem there is, if your step is too small, your model gets stuck. If it's too large, it overshoots and the loss completely explodes. That's exactly why, in practice, developers almost exclusively use adaptive optimizers like Atom. Atom dynamically adjusts the step sizes based on the specific shape of the loss landscape, which keeps your training both fast and stable. Imagine a treacherous, multi-million dimensional mountain range. That is a neural network's loss landscape. It is highly non-convex, meaning it's just filled with jagged peaks and shallow valleys. Adaptive optimizers look at the size of the gradient. If it's large, they take smaller, careful steps. And, crucially, they use momentum. Just like a heavy ball rolling down a hill, momentum carries the model right through those shallow fake local minima, allowing it to finally converge at the true optimal bottom. Section 6. Generalization, guardrails for the real world. Our biggest enemy here is overfitting. Overfitting happens when a model starts to memorize the intricate details and all the noise of your training set, instead of actually learning general, broad patterns. So the model might look like an absolute genius in the lab, but the moment you test it on brand new unseen data, your testing set, it completely fails. We need guardrails to balance our model's complexity so it doesn't just overcomplicate the problem. One of the absolute most powerful guardrails against overfitting is dropout regularization, specifically using a rate like 50%. During training, dropout randomly kills or deactivates half of the neurons in every single mini-batch. Because the network can't just rely on any single fixed pathway to get the right answer, it's literally forced to adapt and build highly resilient, redundant relationships across the entire architecture. But even with dropout, a pretty crucial question remains for any developer. When exactly do you stop training? Because if you train too little, the model underfits. Train too long, and it overfits. The answer is early stopping, and it is way superior to manual weight tuning. As you train, you've got to constantly monitor both your training loss and your testing loss. Early on, both of those curves are going to drop, but eventually the training loss will keep going down, while the testing loss will plateau and actually begin to increase. The exact moment those curves diverge, where your testing loss is at its absolute lowest, that is your optimal checkpoint. You halt training right there to ensure maximum generalization. And just like that, we've navigated the black box. From scaling that single perceptron, applying those vital nonlinearities, running the chain rule backward, all the way to navigating those treacherous loss landscapes with Atom and stopping at the perfect generalized checkpoint. You now hold the core blueprint for deep learning. The real question is, what problem will you solve with it next? Thanks for joining me on this explainer.